Hello, this is Tracy. Welcome back to Math 135, Introduction to Statistics. We are going to continue on in Chapter 3, Topics and Probability. We're going to determine some probabilities. So here we have some sentences, and we want to decide what we think is the probability of that statement, that event occurring. And then ask, can we also determine this probability theoretically or experimentally, or is this strictly a subjective determination for probability? So number one, you will go to work tomorrow. So if that's put to me, well, today is Friday, tomorrow is Saturday, but I don't have enough work done today, so I probably will need to go to campus tomorrow and do some work. So the probability that I'm going to go to work tomorrow is actually fairly high. Probably, I don't know, somewhere between 80 and 100%. That is my subjective determination of the probability that I will go to work tomorrow. Now, could we also determine this experimentally or theoretically? We can't theoretically. There are no rules of probability to cover this situation. However, what we could do is we could look at all the Saturdays during the academic year since I've started, and out of all those Saturdays, count how many of them I've got into work. So we could use that to also determine this probability experimentally. Number two, it will rain this week in Aspen. Well, it's been snowing or raining pretty much for the past week and a half, 2 weeks here in Rifle. Aspen's usually getting worse weather than we are, so I'm going to guess there's a pretty high probability it's going to rain in Aspen. That's a guess. That is my subjective determination of the probability that it will rain this week in Aspen. Could we determine that theoretically or experimentally? Well, there are no rules of probability when it comes to weather, and experimentally, it's really hard to do that experimentally. Even the weather forecasters, what they rely upon is the knowledge, the experience, the relevant know-how of the weather forecasters. So even when the weatherman or the weatherwoman gives us her report, it is still a subjective probability. Number three, what is the probability that you will win the lottery? All right, even if you play regularly, that is still tiny, probably close, really, really, really close to zero. It's not actually zero because, hey, somebody's got to win. Why not you? But it's a really tiny probability. And the way that probability is determined is theoretically. There are rules of probability that allow us to determine how likely it is that somebody will pick those random numbers that win the lottery. So, if it's a tiny probability that you will win the lottery, what's the probability that you will not win the lottery? That is really high. If it weren't a high probability that you don't win, the lottery companies wouldn't make any money and they wouldn't keep doing what they're doing. So what should those probabilities in number 3 and 4 add up to? What should this plus this be? Well, you've got two possibilities. There's the probability that you win, and then there's the probability that you don't win. Oh, let me get some better notation for that. Get rid of all this. So there's the probability that you win, which is, as we've said, tiny. Probability that you win, plus the probability that you don't win. Now, we only have these two choices. Either you win or you don't win, and that is 100% certain. One or the other has to take place, and the number we use to represent a 100% certain probability is the number 1. So complementary events, that's what we're looking at there. E is some event. That means that E prime, the complement, is the event that our original E doesn't happen. If E is some event, E prime is the complement, which is the event that it doesn't happen. And it is always the situation that the probability of an event plus the probability of its complement equals 1, because those are your only two choices. You win or you don't. It rains or it doesn't, with 100% certainty. So here we're going to talk about some theoretical probabilities, how we do some of our calculations. So if we want to find the probability of equally likely outcomes, the probability of one of those outcomes occurring is 1 divided by however many outcomes we have. The probability of one outcome occurring when we have equally likely outcomes, a fair die, a fair coin, an individual card from a deck of 52, is 1 divided by the number of outcomes. If all outcomes are equally likely, the probability of an event E occurring is the number of outcomes in that event, the number of outcomes in E, divided by, again, the total number of outcomes in our entire sample space. So the probability of an event E occurring is the number of outcomes in that event divided by how many outcomes we have in total. So we're going to go ahead and calculate probabilities of some events. So let event E be the event that we roll a 12-sided die and we roll a value greater than 7. Now remember, we already, in the previous lecture, calculated the probability, we already found the space here, the list of outcomes in event E. So the probability of event E occurring is this 1, 2, 3, 4, 5 events or 5 outcomes in event E divided by the 12 possible outcomes. There are 5 ways to roll a value greater than 7 out of 12 possible rolls, and they are all equally likely, so our probability is 5/12. Here, the probability that you flip a coin and get heads. So the probability of getting heads, we have 2 outcomes, heads or tails. They're equally likely. Heads is one of those 2 outcomes. So the probability of flipping heads is 1 out of 2. Now we're going to go back to those 2 4-sided dice that we roll and we add them together. We want to know the probability that we get a sum greater than 5. If you remember our sample space from the previous lecture, we could get a sum of 2, 3, 4, 5, 6, 7, or 8. When you roll 2 numbers that are 1 through 4, those are the only things you can get when you add them up. Now, those outcomes in that sample space are not equally likely. What is equally likely is the different rolls you can get. Here, you can roll your first die be a 1 and your second die be a 1. Your first die be a 1 and your second die be a 2. Your first die be a 1 and your second die be a 3. First die be a 4 or a 1, second die be a 4. First die be a 2, second die be a 1, and so on. These 16 rolls are our equally likely outcomes. Out of those 16 rolls, how many involve a sum that is greater than 5? How many of these rolls have your 2 dice added together to equal something greater than 5? Well, here's 1, 2, 3, 4, 5, 6. So the probability of rolling 2 4-sided dice and getting a sum greater than 5 is 6 out of 16. 6 of these rolls, which are equally likely, give you that sum greater than 5. it is not going to be, well, out of your sample space of, remember S is 1, 2, I'm sorry, your sample space is 2, 3, 4, 5, 6, 7, 8, 2, 3, 4, 5, 6, 7, 8, and your event here was 6, 7, and 8. It is not going to be 3 out of 7 because these are not equally likely. What's equally likely is your 16 rolls. This right here is going to be your answer. Okay, we're going to take another look at complementary events. So here we have some probabilities that were determined experimentally. A survey of 400 people is conducted asking their favorite pet. 250 chose dogs, 100 chose cats, and 50 chose horses. Assuming the sample, survey, etc. are conducted in such a way that the sample is representative of the population as a whole, whatever we figured our population to be, the city of Rifle, the state of Colorado, whatever, assuming we did this well, then the probability a randomly chosen person's favorite animal is a dog is the number of people who chose dogs divided by the number of people in our survey. So 250 out of 400 is the probability that a randomly chosen person will have a favorite animal of a dog. So the probability that somebody has a favorite animal that's not a dog, well, it's going to be 1 minus the probability that that favorite animal is a dog. Because remember, the probability of an event plus the probability of its complement equals 1. So the probability of the complement is going to be 1 minus the probability of that original event. So 1 minus 250 over 400. Subtracting fractions, get a common denominator. 1 is the same as 400 divided by 400. And the probability a randomly chosen person's favorite animal is not a dog is 150 out of 400. Notice we could have also gotten this by adding up the probability of the cats plus the horses, because that's everything that's not a dog. So 100 out of 400 people chose cats. 50 out of 400 people chose dogs. That's 150 out of 400 people. You get the same answer either way. Alrighty, so we're going to go ahead and wrap up this video lecture and continue on the next with more from Chapter